Hello friends, in this video we are going to discuss about the probability of occupancy of donor energy states and acceptor. For that, let us see what was donor energy states. So, as we know from the energy band diagram, semiconductor, that is the intrinsic semiconductor, so this will be the conduction band, that is the minimum of the conduction band energy, that is EC. So this is the conduction band of the semiconductor, and if this will be the EV energy states, that is the maximum energy state of the valence band, and this was the energy gap of the semiconductor, that is EG, and it is for intrinsic semiconductor. Intrinsic semiconductor, then we can say that the Fermi level will be near the middle of the band gap. So this is the Fermi level, that is EFI. EFI means the Fermi level of the intrinsic semiconductor. Now, suppose if we dope this semiconductor with a donor impurity, then the band diagram of the doped semiconductor will look like this. This will be the conduction band minima, that is EC, and this will be the valence band maxima, that is EV, and we have doped this semiconductor using the donor impurities. That's why the Fermi level will be near to the conduction band, because it will be converted into an N-type semiconductor. So I am denoting the Fermi level as EFN. And another energy level will also be created, that is the donor energy level in between the energy gap. So ED is the donor energy level or donor energy states. So we have drawn the band diagram of an N-type semiconductor. After doping with donor impurities, then we have found that an indicator level ED will be created inside the energy band diagram, and where the donor atoms will stay. Donor atoms will reside on this donor energy level or donor energy states. So these black ones are the donor energy. So these black ones are the donor atoms. So the donor atoms are positions on the donor energy states. Now we have to find the probability of occupancy of these donor energy states by the donor atoms. Now let us see what will be the acceptor energy states. So now let us assume that we have doped the intrinsic semiconductor using a p-type impurity or acceptor impurity. If we dope the intrinsic semiconductor with p-type impurity or acceptor impurity, the energy band diagram will look like this. So this will be the minima of the conduction band, and this will be the maxima of the valence band, that is EV. Now since we have doped with the acceptor impurity, so the Fermi level of the doped semiconductor will reside near to the valence band, because it will be converted to a p-type semiconductor. So we have denoted the Fermi level as EFP. Now another virtual energy level that will be created near to the valence band minima, that is like this, and this is the acceptor energy level EA. On this acceptor energy level, acceptor atoms will reside. That's why these are the acceptor atoms. These blue atoms are the acceptor atoms that are residing on the acceptor energy level. So in this way, we can designate the N-type and P-type semiconductor energy band diagram. We can see in the N-type semiconductor, we have created a ED energy level, that is the donor energy states, and in the P-type semiconductor, and acceptor energy states has been created due to the doping. Now we have to find, according to the topic, we have to find the probability of occupancy of this ED energy state and the probability of occupancy of this acceptor energy states. So for that, let us use the Pauli's exclusion principle. So Pauli's exclusion principle states that no two similar electrons can reside in one quantum state. So this was Pauli's exclusion principle that we have already known in the previous lectures. Now this Pauli's exclusion principle is also applicable to the donor and acceptor energy states. Now if we find the probability of electrons, that is the probability of finding electrons occupying the donor energy states, donor energy states, that is ED, or we can say, or the probability of finding an electron in the donor energy states, that is ED, that can be found by P of ED. P of ED means that a probability of finding an electron in the ED energy states, and it is represented by the Fermi-Dirac function in this fashion, that is 1 plus half exponential ED minus EF divided by AT, where EF is the Fermi energy, K is the Boltzmann constant, T is the temperature. This half factor comes from the fact that every donor level has two possible spin orientations for donor electrons. That means we can say that each donor label as two quantum states. As we know that electrons spin quantum number spin quantum number of two different types, that is minus half spin and plus half spin. So that's why we have written every donor energy level as two possible spin orientation, that is plus half and minus half for donor electrons. That's why we can say that each donor level has two quantum states. So the density of electrons, if we want to find, we can write in this form, that is the density of electron occupying the donor energy level will be, if we denote it with small n suffix d, that is the density of the electron, that is n, in the donor energy level for small d, it will look like capital Nd divided by half exponential E capital D EF by KT. This Nd is the donor concentration, and the denominator part that we have written here is nothing, this denominator part is nothing that but the probability of finding an electron in the ED energy states that we have discussed earlier. So we can find the density of electron that is occupying the donor energy level by multiplying the donor concentration into the PED. That is, we have written small nd, that is the density of the electrons in the donor energy level, is equals to the donor concentration, that is the N capital D, into probability of finding an electron in the donor energy states. And P of ED has the value of 1 by 1 plus half exponential ED minus EF by KT. So this half is also called as the degeneracy factor. And this half factor has came due to the two possible spin orientation of the electron. Now, we can also write the Nd equation, that is the density of the electrons in the donor energy level, can be written as Nd, that is the donor concentration, minus Nd plus, where Nd plus is nothing but the concentration of ionized donors. Ionized. So what is ionized donor? That means, suppose we have a semiconductor intrinsic. This is an intrinsic semiconductor, and we are doping this semiconductor with Md doping concentration. Now, if we dope, suppose let us take a value, that is Nd is equals to 10 to the power 16 into 2 per centimeter cube. Let us take a value 2 into 10 to the power 16 per centimeter cube is the doping concentration of the donor. Now, after doping, out of this 2 into 10 to the power 16 atoms per centimeter cube, not all these atoms will be ionized, and we have assumed that only Nd plus atoms has been ionized. So the atoms which are not ionized, they will reside on the donor energy level, and which are ionized, they will give an electron at the donor energy level. That's why we have written Nd minus Nd plus, where Nd plus is the concentration of the donor atoms, ionized donor atoms. Similarly, if we can also find the concentration of holes, the acceptor energy level. So let us find the similarly we can find the concentration of holes in the acceptor energy level. Acceptor energy level, it will be denoted by P suffix A. That will be P is the concentration of the holes for the acceptor energy, so A. So it will also be equals to Na into probability of finding the holes, that is capital P, in the acceptor energy level, that is En. So we can find the equation like this, where Na was the acceptor concentration and P of Ea will have a value 1 plus 1 by G exponential Ef minus Ea divided by Kt, where the G factor is normally called as the degeneracy factor. So we can write G as the degeneracy factor. And this degeneracy factor for the acceptor level, it is G for acceptor level or acceptor energy level, is taken as value of 4 for gallium arsenide and silicon. Is an experimental value for the G degeneracy factor for the acceptor energy level, that is Ea for silicon and gallium arsenide, which has a value of 4. So from this equation we can also write that Pa, that is Pa, that is the concentration of the holes in the acceptor energy level, can also be written as Na, that is the donor concentration, minus Na minus, that is the donor concentration which are ionized. So this Na minus is the concentration of ionized acceptor atoms. Acceptor. So in this way, you can see that we can find the value of concentration of holes in the acceptor energy level, and we can also find the value of concentration of electrons in the donor energy level. And this is P of Ea is the probability of occupancy of acceptor energy level. So we can write this Pa is the probability of occupancy in acceptor energy level, and Ed, P of Ed, that we have already found, P of Ed was the probability of occupancy in the donor energy level. In this way, we can find the probability of occupancy in EA and ED. Now, we can further find the value of ND. So let us take the value of ND. The value of N suffix D, and it was denoted as the density of electrons in ED energy level, and it was written by the equation that we have found, that ND was capital of ND, that is the donor concentration, divided by 1 plus half, that is the degeneracy factor half, and exponential ED minus EF divided by KT. Now if we put the value of ND, we can also put the value of ND here. So further, after, if we take common exponential ED minus EF by KT, then let us multiply the numerator and denominator by exponential minus ED minus EF by it. So in the denominator there was half exponential ED minus EF by KT, and it will be multiplied by exponential minus ED minus EF by. So after simplification, we can find the value of ND, small ND, that is capital ND into exponential minus ED minus EF divided by KT, and it will come as 1 minus ED minus EF divided by KT plus half after simplification. Now this ED minus EF value, that is this ED minus EF value, generally for semiconductor, the ED minus EF value is too much greater than it. Generally it happens. So we can write the small ND will be equals to 2 into capital ND exponential minus ED minus EF divided by KT. So this is the density of electrons at the donor energy level. Similarly, we can find the density of the holes at the acceptor energy level as 2 into Na exponential minus EF minus EA divided by. Hence, these two equations will give the value of the concentration of electrons and holes at the donor energy level and acceptor energy level respectively. So this is all about the probability of occupancy of donor energy states and acceptor energy states. Thank you.